Okay, so the point today is to begin to talk about two-dimensional nonlinear systems. And I'm not going to go into a lot of details with a lot of specific problems, but I want to give kind of an overview of a number of different aspects of nonlinear systems, and then we'll see how far we get and see what we want to talk about after we do this. So some of this is a little bit of a big picture type of situation. So we have been studying linear systems. So a linear 2D system has the form x1 dot is, alpha x1 plus beta x2, and x2 dot is some gamma x1 plus delta x2, so that we can extract this to some form like x vector dot is some a times x vector, where a is this matrix alpha, beta, gamma, delta, right? So this is what we mean by linear system, right? So second order linear system only has first powers of the x1 and the x2 as the two coordinates in the system. So the analogy of something like this for a nonlinear system is to now say that x vector dot is some function of x1 and x2. And so this is sort of how we sort of state the problem, right? So we're stating the problem in this way. And by this function, so we mean by this single line, we mean something like, for example, x1 dot might be the sine of x1 plus 2 over x2, and x dot 2 might mean, minus x1 cubed plus x2 squared x1, right? So that would be a nonlinear system, because we have a trigonometric function, which is, of course, if we Taylor series expanded it, would have higher powers than just the linear power. And we have things like we have negative exponents, right? So this thing in the bottom is like x to the -1 power, so it's not to the first power, right? So being a linear system means it is to the first power. Or we have products of the component of the coordinates, or we have non-first order powers. So these would be examples of nonlinear systems. Now, nonlinear systems can still have fixed points. Okay, so a couple of broad big picture. In, let's say, some region. So if I start with this idea that x vector dot is some function of x1 and x2, I can think of having some particular point, so some region here, say points near some x1 naught, x2 naught, right? So I have some particular place in mind, x1 naught, x2 naught, where I want to consider what the flow looks like near that place. And then by Taylor series expanding my nonlinear system, I can look at just the first order term, right? So if I take this system here and I write down the Taylor series expansion, I'm Taylor series expanding this. So I'm going to do f at x1 naught plus some delta x1 and x2 naught plus some delta x2, I could write that as approximately f at x1 naught x2 naught plus the derivative of f with respect to xi delta xi plus, and I could have second derivatives, right? I squared delta xi squared, and then I would also have in the second derivative a term that looked like xi xj delta x. Well, I guess what I'll do, since I've just got two components, is just write this as x1 x2. Right, so I'd have all these higher order terms. But if I'm going to linearize the system, and so I'm going to be near this point here, the idea is I'm going to throw away these other terms. Right, so when you linearize the system, you can think of it as, you know, what's happening at that point plus the first derivatives as the first thing carrying you away from that region. So if I write this out in terms of components, I would have x1 dot.
So to linearize is to keep the first order terms.
Yeah, it's to keep the first order term.
Okay.
So this is f1 of x1 and x2, and x2 dot, my notation would be, this would be some f2 of x1 and x2. So this f1 and f2, these are two different functions, right? There's a function for the x1 derivative, there's a function for the x2 derivative. So what we're saying here, so this is the nonlinear, and then the linearized version would be at x1 naught x2 naught plus the derivative of f1 with respect to x1 delta x1 plus the derivative of f1 with respect to x2 delta x2 plus order delta squared, and x2 dot would be your f2 at some place things with order delta squared. Okay. And so if I extracted this portion here, I could write this as x vector dot is the function vectors at x1 naught, x2 naught, plus some matrix times delta x vector. And this matrix J is the matrix of partial derivatives of the mapping. So that means that it's what we're going to call the Jacobian matrix. I've written this wrong. That should be a 1 here. So this J is the Jacobian matrix. And we'll say now a couple things about this system, right? I'm going to replace this with approximately equal to, whoa, what did I just do? So this is now the linearized system. Okay. So what we've said so far is that if you start with some nonlinear system, in some region, you can always linearize the nonlinear system by taking the Taylor series expansion and staying in some small region. So within some small region, you can think of the flow as being generated by what's happening at that point, plus a matrix times how far you are away from that point, where the matrix is our matrix of partial derivatives, or our Jacobian of the mapping. Okay, good so far?
Good.
Now, there's two ways to work with this. I want to take this one off of here. This one shouldn't be here, right? Because I put the vector sign on top, so the one shouldn't be there. So if F vector
A Jacobian with the little hat.
I just mean the matrix.
Okay.
I'll take the, yeah, I'm not, I just mean the whole matrix there. So, you got some flow, right? So this is my x1, x2 coordinate system. And so the idea here is if I pick some region in this disk D, if there's no fixed points in D, I can find coordinates which straighten out the flow lines and make the flow lines go straight across the region. And so this is called the rectification theorem. I have rectified the flow. I've made it rectangular. I straightened it out, right? So if there aren't any, so this statement here, right, is the statement that there are any fixed points. If there aren't any fixed points in the region, then you can straighten the flow out to be just straight lines. In other words, and the way you do that is you get rid of this Jacobian. So you can always find coordinates that make the Jacobian equal to 0, and then the flow becomes straight lines. That's called the rectification theorem. So there's always, so this shows up in dynamical systems a lot. It shows up in general relativity a lot. So in general relativity, you like to talk about the free falling coordinates at a given point in space-time. In the free falling coordinates at a given point in space-time, the observer who is in free fall does not feel a gravitational acceleration, and their trajectory is following the natural geodesics of the space-time. And so you can always do that in some small region, and this is a result of the rectification theorem. Right, so it's tied into a whole lot of nonlinear systems, that as long as you don't have something happening which is drawing the points together, you can always find some sufficiently small region for which you can rectify the flow. Now, you might not be able to rectify the flow across the entire region, but you can always find some small region where you can make the field lines or the flow lines go straight.
That's it seems like the calculusing of the flow, which if you look if in like microscopically in small enough
Yeah,
regions,
it looks straight. Yeah, you can make it look straight is kind of the idea. But not just at a point, right? In some finite size region of delta x size. Okay. All right, so that's the first idea. Now the second idea is to do the opposite of that, is to say, suppose that the point x1 naught, x2 naught is a fixed point. Of the flow. Okay, so remember, we're starting with the nonlinear system. X vector dot is f of x1 and x2. And so what we're saying here is that f of x1 naught, x2 naught is equal to 0 means that we're at a fixed point. So now let's suppose that we are working at a fixed point. Then the linear system near the fixed point becomes the following. So if I remember, I said that x1 was supposed to be x1 naught plus delta x1, and x2 was supposed to be x2 naught plus some delta x2. That means that x1 dot is delta x1 dot, and x2 dot is delta x2 dot, because x1 naught and x2 naught are just constants, right? They're fixed places. And so if I come back up here to my linearized system, where I had the Jacobian matrix, the function at the fixed point is 0, and I'm going to replace the x vector dot with the deltas. And so my system here near the fixed point, the system becomes delta x vector is the Jacobian, delta x vector dot is the Jacobian times delta x vector is the linearized system near the fixed point. And we've studied linear systems. So I'll put maybe an approximately equal here, right? And so now everything we know about linear, well, most everything, is to the nonlinear system. Near the fixed point. And that most is an important qualifier. Okay, so we've studied how to work with linear systems. So the idea is if you have a nonlinear system and your nonlinear system has a fixed point, then near that fixed point, the behavior of the nonlinear system may be expected to be like the behavior of the linear system. And there's an important caveat here to this statement about most and what you can learn from the linear system. So once you've linearized the system, there's these nonlinear terms that you're leaving out. So the question is, are those nonlinear terms important? Okay. And the answer to whether or not the nonlinear terms are important. So the linear system is a blank. will the nonlinear system near the fixed point be the same blank? Is the question that we're trying to get at, right? So you analyze so nonlinear systems could be exceedingly tricky to analyze mathematically. So what you do is you linearize them, because once you've linearized them, you just have this matrix, which is the Jacobian matrix, and you evaluate its trace and determinant, and you find its eigenvectors, you find its eigenvalues. And so now you know the linear system is a unstable spiral. So if the linear system is an unstable spiral, will the nonlinear system also be an unstable spiral? And the answer is yes, it will be. Okay, so it turns out that the critical thing is to look at the eigenvalues of the Jacobian matrix. Right, so we have delta x vector dot is the Jacobian matrix delta x vector. So we have lambda 1 and lambda 2 is our eigenvalues of the Jacobian matrix, right? If the real part of lambda 1 and lambda 2 are not 0, in other words, as long as the eigenvalues are not pure imaginary numbers, then the nonlinear system will behave like the linear system. That is the key takeaway. That is something that we want to call the Hartman-Grossman theorem. And I'll write the Hartman-Grossman theorem out in a little bit better phrase. I think there's only one in there. Okay. So this idea that the real part of lambda 1 and lambda 2 not being 0 means that we're going to call the system hyperbolic. So I'm going to move this down here a little bit. I'm going to provide a definition. If the real part for all the eigenvalues is not 0, the system is called hyperbolic. So a hyperbolic system is a system that has non-pure imaginary eigenvalues. And then the Hartman-Grossman theorem says the phase portrait of near a hyperbolic fixed point is topologically equivalent to the phase portrait of the linearized system. And you start to see that we're using real mathematical language. So the Hartman-Grossman theorem is a real provable mathematical theorem. It's not me just waving my hands in the air. So the idea of topological equivalence means that you can deform the flow without breaking it into the flow of, you can deform the linearized flow without breaking the flow in any way or introducing any topological nasty things into the phase portrait of the fully nonlinear system. So we've got the idea of being a hyperbolic fixed point. We've got the idea of topological equivalence. So topological equivalence is, things that you can deform into other things without punching holes in them, essentially, or breaking them in some way.
I was about to ask is if this theorem is proved with topology.
You use ideas from topology, but you don't have to go that far. The Hartman-Grossman theorem is not that complicated of a theorem to prove. I've done it. I've done the proof at some point. The proof relies on the concept of structural stability. So this is also sort of related to the concept of structural stability. So the concept of structural stability, something is structurally stable when the topology of the phase portrait is not changed by small perturbations to the vector field. And of course, that's all tied up into this concept that we've done this Taylor series expansion, right? We've said that x1 naught, x2 naught is a fixed point. Therefore, x vector dot is the Jacobian matrix evaluated at x1 naught, x2 naught times some delta x. Plus now there's higher order terms, right? There's terms that look like a half the second derivative of f with respect to xi, xj, delta xi, delta xj, captures all the terms. If I go through all the terms, I can take this one off of this. Right? So these represent small perturbations. Those small perturbations might influence the vector field, the vector flow. The idea of structural stability, which happens if the fixed point is hyperbolic. So if the fixed point is hyperbolic, then it's structurally stable.
Just curious, in that first in the Taylor series expansion that you just did, why didn't you include the first order?
Because I'm working around a fixed point. The first order term is 0.
Okay.
Okay. So now, let's remember that lambda being something like lambda plus or minus being plus or minus 3i. Corresponded to a simple harmonic oscillator, or what we call in dynamical systems theory a center. In centers, we have these nested closed orbits, and we have a fixed point at the origin. Any perturbation that you make to a simple harmonic oscillator is likely to destroy the simple harmonic oscillator and turn it into a damped spiral, right? If you add any damping at all to a simple harmonic oscillator, it ceases being a simple harmonic oscillator and it becomes a damped spiral, right? So if you perturb this, what you get is a spiral. So this is why centers are not structurally stable, right? Any perturbation is going to add to any perturbation to the system is going to basically knock it out of being this little simple system and cause it to drop into some sort of spiral. On the other hand, if you start with a spiral, and then you perturb it, and you start at the same spot, what you end up with is a slightly different spiral. You can't just nudge a spiral that's, say, stable and turn it into a stable node. You can't nudge a spiral that is unstable and turn it into a stable spiral. You can't nudge a stable node, right? So if you start with a stable node, so here a stable node means, you know, I'm coming in, say, this way. Right? If I perturb my stable node and I start up here, I'm still going to end up down in there, right? I might get a slightly different looking stable node, but I'm not going to bounce the stable node into something completely radically different under a small perturbation. I'd have to do something major to alter the system to change a stable node into something else. That makes sense? Whereas if I started with a center and then I perturbed it at all, it would drop into a spiral, one way or the other. Okay. So that's sort of the first point. So the first point is to understand that if we're thinking about nonlinear systems, so if I'm thinking about some general nonlinear system, the first question is, I can obviously linearize the nonlinear system. One thing you can do with the linearization is you can introduce the rectification theorem. But in dynamical systems theory, what you normally want to do is not look at one small region. You want to kind of look at a bigger region than what you would do in a rectification theorem. So the question becomes this question. Suppose when you study the linearized system, you get a something or another. Will the nonlinear system also be that? And the answer is yes, it will be if the fixed point was hyperbolic and had non-zero real parts of the eigenvectors. So the hyperbolic means that you have either incoming or outgoing part of the flow. right? So when I look at the eigenvectors, you know, number plus number times I, real part of the eigenvector plus I times the imaginary part of the eigenvector, right? If that real part isn't 0, then it's either flowing in or out. That imaginary part tells me whether or not it's flowing around. So as long as the real part is not 0, the system's going to be structurally stable. And that means that any, the linear system is a good representation of the nonlinear system, because with the structural stability, any perturbation that came from this nonlinear part that I've excluded. So here's my linear part of the system, right? So this thing, this dot here, that box, that's my linear system. This other part here, that's my perturbation. If my linear system is structurally stable, then the perturbation is not going to change what the system's doing, is the idea. Okay, so as long as I'm not in one of the centers or one of the other funky cases, right? So there were the line of fixed points, the degenerate fixed points. There were these other cases in 2D systems where the fixed points come together. They don't come in apart in different axes. There were these weird cases, and there were centers. As long as you're not one of those, the system will be structurally stable, and and you'll get the non-linear system will look like the linear system near that fixed point. All right, that makes sense so far?
Yep.
Okay, so that was sort of lesson 1. So I'll write that down. Lesson 1. Knowing how to handle linear 2D systems tells us what to expect in nonlinear systems. Near fixed points. So that's sort of lesson 1. All right, now the second lesson in this all right, so if I come back to classical mechanics and I think about Hamiltonian systems, not all systems that one studies in classical mechanics can have a Hamiltonian written for them. So for instance, the damped oscillator is not a Hamiltonian system. You can't write down a Hamiltonian for a damped oscillator, right? But Hamiltonian systems are really important category of what we think of as traditional classical mechanics. Now, as sort of a sidebar here, nonlinear dynamics is sort of a bigger picture.
Maybe an attempt to track.
Yeah, this isn't gonna work if I put this over here. Let me move all this. Let me just erase all this. So what I'm going to say, and I'll write this into the notes, right, is that nonlinear dynamics is a slightly bigger set of problems than traditional classical mechanics, right? Traditional classical mechanics systems tend to be Hamiltonian systems. And so Hamiltonian dynamics is a subset of nonlinear dynamics, but it's a kind of small subset of nonlinear dynamics. So nonlinear dynamics is broader than Hamiltonian dynamics. And what I'll say about that is that largely the people who are studying nonlinear dynamics as physicists are studying mostly condensed matter theory. So the people interested in these types of approaches to theoretical physicists are into theoretical physics are largely condensed matter theoretical physicists. They are there are some people who are relativity people. So general relativity is also a nonlinear classical theory. And so equations in general relativity can be studied through the lens of nonlinear dynamics, right? But condensed matter systems, biophysics systems, fluid mechanics systems, all fall under the big umbrella of condensed matter theory. And so nonlinear dynamics is that bigger picture. And classical mechanics and Hamiltonian dynamics as sort of the exemplar of classical mechanics is a subset of nonlinear dynamics. So that's what I want to say about that. Okay, so now in Hamiltonian dynamics, we started the semester in Hamiltonian dynamics we proved the Louisville theorem. Which says that under Hamiltonian flow, the volume of phase space is preserved. Right, so you know the picture in Hamiltonian dynamics, you know, that you have some region here and you have some flow, and that flow might distort the region, but it's going to have the same volume. The volume of D2 will be equal to the volume of D1. Now, Hamiltonian dynamics, though, if you look at it from this larger picture of, even if it's nonlinear Hamiltonian dynamics, if you look at it in this bigger picture, all of the dynamical systems which are structurally stable, that are hyperbolic, that have fixed points, are not volume preserving. So Hamiltonian dynamics tends to fit into the pictures of the centers, right? So Hamiltonian dynamics does not tend to fit into this structurally stable hyperbolic fixed point type of world. Okay. Now, there's still interesting nonlinear Hamiltonian dynamics problems. So, for example, if I do the pendulum, at non-small angles, then I have the system So let's suppose that here's my pivot point, right? And I have some length here and I have some mass at the end. And this is my angle theta. Then the pendulum at non-small angles works out to be this equation, which you can write down a Hamiltonian for, and you can drive Hamilton's equations of motion. You can write down potential energies, right? So that there is a Hamiltonian, right? A sum of kinetic and potential energies for this system, right? The energies conserved, all those types of things, right? And so this is my pendulum at non-small angles. And of course, if I linearize the sine, so here's my sine of theta, right? So this is not linear because I have this sine of theta in there, right? And if I make a small angle approximation, then of course I get my simple harmonic oscillator equation, right? If I do sine of theta is approximately theta, then I get d squared theta dt squared plus g over L theta is equal to 0. So I can get to my linear problem. Right? So if I make the small angle approximation, I can linearize the system. But if I don't linearize the system and I work with this full nonlinear system, I have a Hamiltonian system. And I can do stuff with it. All right, so anyway, what can I do? So let me define nu to be theta dot. Then the equations become theta dot is nu dot is minus the sine of theta. Okay. Which is not all that interesting. Now, if theta is 0 or pi, or basically n pi, right? We have fixed points. Okay. If I look at what the phase portrait of this thing looks like, if this is pi over here, and this is minus pi over here, what I have is a trajectory that connects these 2 points. And then I'll have another trajectory that connects these 2 points. And these trajectories correspond to starting here and swinging around one way or swinging around the other way. So it's basically, those are the trajectories for vertical to vertical swings. And the time to go from here, here's the pivot, all the way around is actually infinity. So you don't, so if you start at this point and you follow this trajectory, you get to this point over here, but you don't keep going. All right, it actually takes an infinite, you can compute and show that that takes an infinite amount of time. So, or you can go the other way. If you have any amount of energy less than that, we have trajectories that look like these. Now, these orbits here that take the infinite amount of time to go around are called homoclinic orbits. And this is new in 2D nonlinear systems. There are no homoclinic orbits in linear systems. In linear systems, there's centers, there's spirals, there's stable nodes, there's saddles. But the idea of a homoclinic orbit is a completely new thing, which has come from the nonlinear system. And in fact, homoclinic orbits are common in Hamiltonian systems. So even though we're studying Hamiltonian systems, which are this type of system which in some ways are not the full richness of nonlinear dynamics, there are still other interesting things in nonlinear Hamiltonian systems, right? You get these ideas, homoclinic orbits, for example, are a common thing that can show up in nonlinear Hamiltonian systems. Okay, so for instance, we might have a system, we might have a full nonlinear system for whom the phase portrait has, say, a saddle here. So that's a structurally stable element. And I might have over here a center. And then what I can have is a homoclinic orbit that connects to what is locally a saddle. So the full phase portrait would look something like this. Where the homoclinic orbit is separating a region that has closed orbits inside it from a region that's outside for which there's a saddle sitting next to it. So a nonlinear system, so if we were studying a particular nonlinear system, we would see that there was a saddle and a center. We see, okay, there's two fixed points in the system. One of them is a saddle. That saddle is structurally stable. The homoclinic orbit is actually pretty structurally stable as well. The center is not, right? So it might, if we perturb the system, the homoclinic orbit might stay in place, but the center inside of the homoclinic orbit might become, say, might become a stable spiral. I could redraw this into a stable spiral. Yes, that could be true. Right, so if I perturb this system, so I start with this system here and I perturb it, I'm going to copy the whole thing. So under the perturbation, what I can do is knock out these stable closed orbits in here. I'll keep this here, but anything that's coming off of here would spiral down onto there. I could fill the whole region. So if I trace forward, if I'm inside that blue homoclinic orbit, anything I trace forward in time ends up at that stable spiral location. Anything that I trace backwards in time ends up on the homoclinic orbit. Trace any trajectory. Can't spell today. Inside that goes to the fixed point. And if I trace any trajectory inside the homoclinic orbit backwards in time, I go to the homoclinic orbit. Okay, see how that works out? Writing lots of notes. Folks, good?
Yeah, good.
Wherever you
Just
still
a
with
lot of
us?
writing.
I'm good.
Yeah, okay, now, even in nonlinear Hamiltonian systems, it is very common that they have time reversal symmetry. So one very common feature of Hamiltonian systems is that they will possess time reversal symmetry, which means the following thing happens in the phase portraits, right? If this is the positions and this is the momentum, and up here you have some trajectory that looks like that, under time reversal, you end up with a flow down here that's the mirror image around the x-axis.
So it doesn't mean exactly time reverse as if you were to
No,
stand.
it really means time reverse. So if I go back up here to my example of the Hamiltonian system here, right? So theta dot is nu. So the nonlinear oscillator. So theta dot is nu dot is minus G over L sine theta. So what I mean by that is if I take T goes to minus T, I get the system back. That the system is symmetric under time reversal means you can take T to minus T. So now if I take T to minus T how do I do this? Then theta dot, which is d theta dt, would go to minus theta dot under t goes to negative t. Try to put this down here.
For a second, I was thinking about CPT.
And then nu dot is minus g over L sine theta. That's equal to d nu dt. So that's going to go to d nu dt is now equal to minus g over L sine theta. Now this should work if I do this, if I think about this the right way. So what I'm going to do is say that t is equal to t twiddle. Theta dot is theta twiddle, and nu dot is going to be minus nu twiddle dot. So I haven't done this recently, so I'm tripping over it a little bit. So I have theta dot is nu. Okay, so theta dot becomes theta minus theta twiddle dot. So that's apparently equal to nu. And then, oh, but nu is d theta dt. That's how I'm going to get away with it. Nu is d theta dt, right? So nu twiddle is minus d theta
D theta twiddle?
dt, which means is equal to, all right, so we should like work out why this works. T goes to minus t, nu needs to go to minus nu is time reversal. Yeah, that's, oh God, how do you make this work? So if you time reverse, things have to move backwards. All right, let me try to say it that way. I'm going to come back to here. I'm going to erase all this crap because I think that I've said this maybe not the best way. So what do you mean by time reversal? When you reverse time, the time goes backwards, but so does the velocities. So time reversal means that you run the clock backwards, but you also run the velocity backwards. All right, that makes sense? This is gonna, yeah, now this is gonna work.
You can look at your dynamical variables and see what happens to them.
Right. So when you reverse the time, you reverse the velocity direction because the velocity is d position dt. Position is a spot, but a velocity is how you're moving relative to the spots. So if you reverse the time, a movie that was running with the object looking like it was moving to the right, if you run the movie backwards, it looks like it's moving to the left. Okay, so time reversal symmetry, you send t to negative t and nu to negative nu. So now if I take this equation here, which is d theta dt is equal to nu, well, that shows time reversal symmetry, right? Because if I take t and I make it a negative t, so if right here I put it a negative t, then on this side, I have negative d theta dt. And on this side, I'm going to put in negative nu, right? So when I do time reversal symmetry, I take the original formula and I put a minus sign next to every t, and I put a minus sign next to every nu, and this is the same as d theta dt is equal to nu, right? So I didn't change the equation by putting a minus sign in front of both t and nu. That's the way to think about it, right? So time reversal symmetry, you put a minus sign in front of every t and in front of every nu, or every velocity. So this first equation shows time reversal symmetry. So does the second equation. The second equation is nu dot, which is d nu dt, is equal to minus g over L sine theta. All right, so when I do time reversal symmetry over here, there's no change when I send t to minus t and nu to minus nu on that side. But on this side, I put a minus sign up top and a minus sign down bottom because I send t to minus t and nu to the minus nu. And so I get time, so those two cancel off, and I have the same equation again. So the nonlinear oscillator exhibits time reversal symmetry. Okay, that sort of makes sense. And one way to say this is that no spirals have time reversal symmetry. Right? If you draw a spiral, they are not up-down reflectance. Spirals don't have time reversal symmetry, whereas homoclinic orbits, centers can have time reversal symmetry. Saddles can have time reversal symmetry, so can nodes, potentially. They don't necessarily have to, but they could have time reversal symmetry. But time reversal symmetry is a built-in feature of classical mechanics, of Hamiltonian dynamics. It's built into Hamiltonian dynamics that you have time reversal symmetry, which is sort of tied into everything else. All right, so we're going to stop. And the